Hi, my name is Chris Christensen. I'm the Director of Education for Noria. I'm very excited to offer a new way to access our trainings through live online training. Students in the live online courses can ask the instructor questions, see close-ups of equipment, and tool demonstrations. Our goal here is to make training more accessible to you and your team. We will be hosting public online events throughout the year, so check out our training calendar on our website for dates and times. And if you want us to, we can also provide this training to you and your organization. This is ideal if you need to train staff located in different areas of the country. It's our goal to bring the same quality training right to you at your computer. Now, let's take a look at a segment from one of our live courses.
So as we're discussing with erosive wear, this is where we have particles that have a velocity associated with them, and they're going to impinge upon machine surfaces. And this is most prominent in hydraulic systems, where you're going to have that velocidal approach to the particles, and it bounces off of a sharp corner or through valves as it goes through the actual machine. So you got to be careful with how many particles actually get in your machine for this. Now, when we talk about particle contamination, one of the more important aspects that we need to look at is the physical size of the particle that is contaminating our machine or our fluid. So as you see on the slide here, we're looking at different diameters or common diameters of particles or of things that we can relate to. A human hair, if we took a human hair, cut it in half, and looked at the diameter of a human hair, it'd be somewhere around 80 microns across, all right? Now, the smallest you can see with the naked eye is about half of that, around 40 microns. If you've ever been in a dark room and had like a projector set up or maybe a bright light, and you see the fuzz and the debris floating in front of that bright light, that's the stuff that's around 40 micron in size. It's very small, it's just kind of airborne, and it stays airborne. Now, as we go down in size, you see white blood cells, talcum powder, bacteria, things of that nature. We're getting smaller and smaller sizes, down to bacteria, 3 microns in size. Remember what we talked about with elastohydrodynamic lubrication. Those lubricating films are 1 micron and less. So bacteria, algae, things like that grow are bigger than a lot of our lubricating films. And as we discussed previously, it's the particles that are roughly the same size as the lubricating film that cause the most damage. So if we had a very simple demonstration here or picture here, we've got a bearing, right? And this bearing's rolling, around the race, and we've got a particle. And this particle is very large, all right? Let's say that this is around a 40 micron particle or something. The size may be such that it's so big that this bearing is just going to push this particle along, or it's not going to allow it to actually get in the fluid. Now, over time, this particle gets captured, right? It gets pressed on or something like that, and we start to crack this particle, right? It starts to break down. Then all of a sudden, we've got a particle that is going to be roughly the same size as that lubricating film, right? And remember, this is somewhere around 1 micron. So something very, very small. It gets in here and it starts to cut, and this is what leads to little debris that looks like crescent moons, or in some cases, it's little curly cues like this. So the wear is caused by the small particles. Like we see in our table here, the smaller the particle size, the more of them we have in the fluid. They build up over time, they're made, and these are the ones that are the most damaging. It's the stuff that's around 10 microns and smaller, stuff they'll call silt-sized particles that cause the majority of machine damage. So these are the ones that we want to pay attention to. Remember, if you look at a container or a jug of oil and it looks clean, right? We don't see anything floating through it. It may actually not be clean enough for what our machine needs. If you can see particles in it, the stuff that you see is not the stuff that's the most dangerous. It's the stuff you don't see. So one side of the coin is how big or how small the particles are. The other side of the coin is how hard they are. So when we talk about particle hardness, a common scale that we use, and you can see it on your screen here, is what is called Mohs. And Mohs is a scale used in a lot of different minerals and gems to define how hard something is. It's not tested like Rockwell hardness or Vickers or something like that. So this is very empirical. It's basically what scratches something else. Now, on the low end, on a Mohs scale of 1, you've got something like talc, something that's very, very soft, something that can scratch easily. On the high end, the 10, the scale goes from 1 to 10, you've got diamonds, all right? So everything falls in between that 1 to 10 scale. If it's a higher number, it is harder, all right? It can scratch it. It is more abrasive. So we see iron up here has a Mohs scale of somewhere around 5. We know machine parts made of iron. Now, as we do move into high-speed steel, right, bearing materials, things like that, now we're into a 6 or 7, a little bit harder. Of course, steel, harder than iron with the addition of carbon and other alloys. Well, of course, diamond, number 10. And then we look here at silica dust. Remember, the majority of contaminants that we talk about is nothing more than dust. It's dirt, right? That's what's getting in there. And most of your dirt is comprised of silica. Now, everyone's dirt's going to be a little bit different. The dirt here in Tulsa, Oklahoma, the red dirt, we have a high amount of clay, silica, and stuff like that. When you get into areas like Minnesota where you have more blacker dirt, right, now you've got silt in some of those areas. But if we're looking at this in an oil analysis report, we're going to trend silica levels as well as aluminum levels. So silica and aluminum, as they trend together, that is very indicative that you have got dirt contamination inside your fluid. And our blurb down here at the bottom, particles of high compressive strength or hardness and angularity cause the most damage. If you look at dirt under a microscope, it has a very crystalline shape. It's got very hard defined edges, so it cuts incredibly well. An exaggerated example of this is a failed bearing that I've got over here. So if you're looking at this bearing surface, you'll actually see these raceways, the scoring in the bearing surface itself. This is where you've had particles that got in here and started to cut and gouge and remove that material over time. So as this builds up, as those particles get more and more embedded in there, it removes more and more material. And this is what subsequently leads to misalignment, failure, all these other association things with particle contamination. Now I'm getting signaled that I've got a question.
Yeah, Wes, I've got Josh here, and he's asking the question about the sources of those contaminants. Where are they coming from?
Sure. All right, Josh. So your question about where the contaminants come from, they come from the entire life cycle of that lubricant. The term that we use with contaminants is ingression. And ingression is all the contaminants.
With your registration, each student will receive a full color printed manual, access to our learning management system, which is going to include recordings of your class that you just took, a PDF of all the course slides that you can reference, and other materials that would be beneficial to you. You're also, if you're enrolled in one of our certification courses, going to have access to the Noria Academy app. So remove the barriers and attend a live online course today. You can call us at 1-833-273-6518 or come by and visit our website at www.noria.com for more information.